Hello, everyone. Welcome to the DevOps conference. And for our first talk for today, we'll speak about scalable architecture from the ground up. And our speaker, Oren, will present it. Hey,
Hello.
hello, Oren. How are you
Hi.
doing today?
I'm doing very well. Thank you.
Awesome. And Oren is one of the founders of RavenDB NoSQL database. And Oren, can you tell our speaker, our audience a bit about your previous experience with scalable architectures?
Um, I've been building RavenDB itself for the past 12 or 13 years, and it came from working with organization and environments where you had the need for high performance, high load, and the current tools weren't up to the task. And it's interesting because a database is just one component in a much greater a team or approach to actually solving the problem. And one of the things that I noticed in recent years is that there is this tendency to just throw money at the problem and get a bigger machine, get more machines and stuff like that. And I think a lot of that has been lost to the concept that, okay, Amazon or Azure or Google have enough compute capacity. I can just pay for that right now. There was recently a post on Hacker News where someone didn't define indexes on the database, which meant that every query did a full table scan, and that actually cost them money on the cloud. So they paid $5,000 for basically no reason. If they had an index, everything would work just fine. And this is a really obvious example, but I think that in many cases, if we're talking about architecture that need to scale from 10 users to 100,000 users or to 100 million users, people tend to assume that, okay, I have to go with a high degree of complexity. I have to accept uh, uh, a high limits on what I can do, all sorts of stuff like that. And a lot of that is just about figuring out how you can do things properly the right way around. And that's basically what I hope to present today.
Great. Maybe we can just dive deep into your presentation. How
I
about
would
that?
be I would be very happy to start. Yes.
Let's start it then.
So to the audience, my name is Oren. As Michael has mentioned, I've been building RavenDB for a long time, and I'm here to tell you about how to build a scalable architecture. The assumption here is that you want to come out with some system that needs to process a lot of requests. And I intentionally use the term request here and not data. Big data solutions tend to have very different constraints and requirements. If I have to go over 2 petabytes of data, that's something that no human is going to wait for. But if I have to deal with 50,000 requests per second because I don't know, I'm selling the Mona Lisa and I need to accept all of those people, that's something quite different. So before we get started, I want to give you some idea about what is actually involved. And what is actually involved in what is capacity, what does it mean to have scalable? And there is this terminology that I really like, which is that a scalable system is that you add resources and the capacity increase in a proportional manner. So if I add if I double number of servers that are working on the problem, I should have double the capacity. A system is not scalable if this is not the case. If I double the number of servers and I got 50% better capacity, then very quickly I'm going to end up with, okay, I double it again and get zero additional capacity. Now, there is one surefire way to have a scalable architecture, and it's a very simple one. Get a time machine. And this is the basic idea. You have a time machine, you deploy the service, you make some horrible mistakes, you go back and fix them. repeat, you're done. You have a scalable system. Unfortunately, my time machine is back ordered, so I have to do without that. The nice thing about this is that you can learn from other people's pain. So there is a lot of literature and talks that talks about how to design big complex systems. There's also a lot of postmortems. What are the things that did not work? Now you can go and copy the same architecture and the same lessons that were learned by other teams. But there are a couple of things that we have to take into account when we're doing that. The first issue is that your scenario is different. Your scenario is unique. At least you hope that it is. It might be very similar to what you see in other places, but for the most part, things change and evolve. In Twitter, for example, both hashes and mentions were not something that was created by Twitter itself. Users started using them. At one time, there was a lot of unofficial Twitter clients that adopted these conventions, and eventually Twitter adopted them directly. But think about what it means in terms of how it feels like inside of Twitter. Our users are pushing us in a completely different direction. We did not design for that. We did not think about that. And now we have to adapt. So a key aspect when we're talking about this is that we have to remember that we have to be adaptable. And a lot of that is about the architecture. A lot about it, how do you put down the infrastructure that you have in order to be able to do all sorts of interesting things. Now, let's talk about a somewhat simple example. I need a certain operation in maybe user registration, login, posting something on Twitter, placing a bid, whatever that is, to be fast. And there are two ways that I can do that. At the micro level, I can optimize a particular operation. I can make sure that I have the appropriate storage scheme for that. I'm doing macro optimization at the assembly level, a bunch of other stuff like that. And that can help. But micro optimizations can only take you so far. Eventually, you have to deal with the overall architecture. And as it turns out, a proper architecture can cover a lot for you. It can make sure that you have the time and the capability of fixing the mistakes that you will assuredly make. Now, I'm not here to invent something completely different. If you have paid any attention to architecture in the past 20, 15 years, domain-driven design and command query responsibility separation are both things that pop up very frequently. In many cases, they are used as, in my estimations, as buzzwords, things that makes things more complex. Oh, you have to have this strict separation, and now I have to write. The user wants to update their name, so no, it has to be a command. It has to be processed by a command processor. It has to go into the write-only database. There is an ETL background process that would go and change that and push that into the read-only database, and the whole thing just became, okay, I want to update one field, and that's going to take me 3 weeks to fix that. That is the kind of complexity that you generally don't need. But what do you do? And the number one rule that you have to first figure out is, what is my commitment? What is it that I'm actually doing? So let's talk about this. SLA stands for Service Level Agreement. What did I commit to the business, to the user, that I will, what is the time limit for me to do something? Now, a really good example of that is when you have this statement: page load in under 200 milliseconds for 99.99% of the users, which means that for one page load out of every 10,000 is allowed to exceed 200 milliseconds. This is expressed in terms that I like. Why is that? Because it is measurable and actionable. Now, typically, what is page load? What is it 99% of the users, or is it 99%, 99.999 of the page load, or a bunch of other things that you have to nail down? But the key aspect here, it should be something that is measurable. And it also means that as part of almost the very first thing that you're doing in the system, you should have metrics and reports and the ability to say, am I actually meeting my SLA? To start with, you have to define what is the SLA. Sometimes this is something that the business says, oh, we have to do that. Sometimes this is something that is dictated by contracts. At one point, I signed a contract that says that a standard business transaction had 5 seconds to complete, and a complex business transaction had 15 seconds to complete. I was feeling very good about myself because all of the transactions in the system completed in under 100 milliseconds. It turns out that no one cared. I could have taken 30 seconds. They would have noticed. But setting those goals for me means that I understand what I can and cannot do. And this is important because it is very easy to get to a point where you have made promises that you cannot deliver. What does it mean? Let's assume that I have a certain operation. I need to process an order for, I don't know, for a cup of coffee. I need to process that within a certain amount of time. Now, here's the problem. I'm relying in processing of the coffee on the barista, on Visa for payment processing, and I also need to talk to, I don't know, health and human services to make sure that I'm not giving you something that you're allergic to, whatever, just throwing stuff out. Can I actually implement all of those features as is within the given time constraints? Well, maybe Visa is good. The barista I control. But Health and Human Services is a government agency. They require me to send them a fax. I cannot meet 200 milliseconds SLA. And I want to be able to know that as soon as possible so I can say, hey, problem. I'm not willing to accept this feature. And at that point, you typically have a discussion with the business. The business may say, oh, I really have to have this feature. So I'm going to relax the SLA. Or I'm going to say, oh, we cannot have this feature if we touch the SLA because the SLA is sacred. Notice that in either case, this is a business decision that you brought up. And this is important because if you accept this feature, you may end up in a situation where you're the one holding the bag. You're the one that has to meet both the SLA and the feature. And then you end up with tremendous complexity. Now, this is not strictly an issue of the architecture. This is an issue of what is the system feature set that you accept to do. But if your architecture tells you, hey, this is a problem, then you can approach that in a much better way. So let's see some of the things that are going to kill me. So the number one is that I'm doing some critical work, some expensive work in the critical path. Now, what is a critical path? Rendering a page, processing a request, replying something. If I know that I have a 200 milliseconds budget, and I have alerts on that. Hey, this request took too long, and here's the things that he did internally. That's something that I would rather avoid, and I can figure it out. Now, in many cases, the sort of things that are expensive are well known. So I have to go to a database and run some really complex query. Give me all of the orders for these users who also order things from a similar user, and that is a tree-level nested join over a subquery operation, and a whole bunch of other stuff like that. What happens then? Well, what happens then is that this is going to take a while. Now, here is something really interesting. You're sitting there writing code and very happy with yourself. And you're able to meet your own SLA. The problem here is that you're doing that on your own instance as a single user. The actual time that you have is a lot less than that. Let's think about that. I have an 8-core machine, which means that every second I have 8,000 milliseconds. If all of my requests are taking 200 milliseconds, I can process 40 requests per second per machine. Honestly, if this is completely independent, I can just add more machine and have infinite scalability. But to be perfectly frank, 40 requests per second is 40 requests maximum per second is horrendous. Just to give you some numbers, I have a Raspberry Pi here. I can process thousands of requests per second on that. I think the maximum that I reach on a Raspberry Pi 400 is something in the order of a 7,500 requests per second. Raspberry Pi 400, that's 4-core machine with 4 gigabytes of RAM. So if your system is able to handle only 40, that's a problem. Now, a lot of time you're doing really complex stuff. You're composing details from many different parts of the system. You're calling to third-party services, and all of that has to fit within the time limit. And it's, you promise, yes, I will be able to do that. You cannot do that. This is not going to actually be possible for you to make it happen. So we have to rethink how we're doing that. Now, if I have to buy something that I can't afford, how do I do that? I have a payment plan. I get a mortgage, I get a loan, something like that. So we have to make a determination. What is cheap and what is expensive? Cheap things are looking up by ID, by a simple index, querying the local database. I have a well-defined amount of work that I'm going to do. I can throw stuff into a queue. All of those things are really, really, really cheap. In the order of, I would expect to be able to process thousands of them per second on a single machine. The expensive things we already looked at, third-party queries, complex queries, stuff like that, and processing lots of data. Now, so don't do expensive things. Just don't, and you're scalable. By the way, an interesting side effect, if all you're doing is cheap operations, you're both performant and scalable, which are two independent and somewhat contradictory things. What do I mean? You can be highly performant, but not scalable because you're tied to a single instance. You cannot get more capacity in this way. Or it can be highly scalable, but slow. But if you are limiting yourself to doing the cheap things, this is easy. Now, my father once told me, buy low, sell high, and this is how you're going to get rich. And this is one of those statements that I'm going like, huh? I mean, it's true, but there is so much that this doesn't cover that this is absolutely insane. So the question here is, okay, I can build trivial systems, easy, but how do I build the facilities and the things that I actually need to deliver real-world value? I mean, I can do a to-do application, great, but no one is going to pay me to do a to-do application. And honestly, most to-do applications don't need to be scalable. So what do I actually have to do? By the way, OneNote, which is interesting, this is a to-do application, and this is an insanely scalable system, and they have some really interesting architecture. But maybe I would have time to touch on that later. So let's talk about this. I still need to do the expensive things. I still need to do it at some point, but I don't need to do it right now. I don't need to do it in the critical path. Instead, I can throw that into a queue. Let's say that I'm processing, again, orders for coffee. So instead of doing all of the background processing that I need to do, authorizing against Visa, going to looking at the allergy and the health services and whatever, I'm not going to do that while the user is waiting. Instead, I'm going to throw that into a queue. And a queue is something that is trivial to scale. A distributed queue is actually a really interesting exercise in how you build and manage that. Both because it has a lot of that, but because it's conceptually very simple. And no matter where you are, you will always have some queue available to you. SQS, Azure queues, GCP also have something, Kafka, RabbitMQ, whatever. Queues are always there. So if we are if throwing something to a queue is cheap, then that meant that I have successfully deferred the amount of work that I have to do. So I can accept a lot more work. In the real world, this is a Starbucks model. You go to a Starbucks, there is a cashier. They take the order, they take your money, and then they move to the next customer. You're not waiting at the cashier to get your coffee. Instead, you move to the line where the barista or multiple baristas are going to be operating and preparing your coffee. And you know what? If you run out of milk, you're still able to continue processing orders. The separation of accepting work and processing that is key. It also means that for the most part, most of the things that I expect a user to sit in front of, either directly or indirectly, are not going to be doing any work. They're going to do the cheap things. Those things are going to operate over data that was already prepared. They're going to be doing only the things that are known to be cheap. Now, this is very much like CQRS, but instead of seeking the responsibility separation, I'm separating this by what I can do to meet my latency targets and what I cannot. Now, remember that how I actually do the work and how I present what I'm doing is something totally different. So again, McDonald's right now have a lot of online kiosk that you go and you order and they start making the food. And in the meantime, you have this screen that says, oh, order number 2101 is in preparation. Order 2101 is ready, stuff like that. In the same sense, you're going to do the same exact thing. You accept something, you record that you have accepted that, and then you just wait for that. And that's really important. Because from the user perspective, there is a difference between I'm waiting for you on hold, basically, and thank you, I got that. We are processing, we'll get right back to you. And in most cases, that means that the front end doesn't have a lot to do. So it's simple, which means that I can do more. There is a lot of user experience concept to deal with here. But the whole idea is that I'm splitting my system into what is almost just the CRUD, just do the trivial things, and the backend, which does all of the heavy lifting. That means that I'm always almost going to work on prepared data. That means that I don't really have a lot to do in the front end. And by the way, in the front end, I'm not talking about just JavaScript running in the browser. I'm also talking about anything that processes those requests on your web servers. And at the same time, I have this freedom to do more, to spend more time on not trying to tie backend and frontend together and meet all of my deliverables. Because I created this moat in the middle, the thing that I can and cannot do. Now, a really important question here, why not just use autoscale? Every single cloud and Kubernetes and wherever you want have some feature like that. If my web server hits 75% utilization for some time, spin your node, rebalance traffic, you're done. And vice versa to auto downscale. Why not go with that? That's simple, right? Well, sort of. And it works. But it only works if what you can do, if your limit is serving requests. That's typically not the case. In some cases, if you're doing, I don't know, server-side rendering, which is compute bound, which sounds pretty strange to me, but may happen, you may want to do something like that. But for the most part, that's not the limiting factor. You need to run complex query, touch a lot of data. You need to scale up your database. And scaling a database is not something that you do trivially. Now, RavenDB can do that almost faster than any other database that I know of. And it takes us about 5 to 7 minutes to scale you up. Other databases, Elasticsearch on Amazon, for example, if you want to scale up your search instance, you have to do something called a blue-green deployment, which basically means that you have to create a whole new copy of all your data and all of your instances at the new size, copy all the data, and then switch over, and this can take days. So what about other people? I'm dependent on others' validation for Romania. I don't even know who is handling that because that goes through 3 different intermediate services. I cannot expect them to, I now have a big cell in Romania, and suddenly I'm flooding them with all sorts of others validation requests that for some reason they take a lot of time. They can't autoscale. And finally, and crucially, at the other side of the screen, there is this guy going like this. Well, what about this? What about this? What about this? Now, there is the timeout for the request, which is typically 15 seconds. There is the timeout for the user's patience. There have been many studies on that, and you have about 500 milliseconds to do something before the user wants to switch to something else. You have about 10 seconds before they actually switch to something else, during which time they are pissed off at you. And it's really interesting because UI considerations, switching the cursor to the spinny things, accepting this and saying, okay, we'll get back to you, give you a much better feeling because you no longer have to just wait like this. Amazon and Google both had studies about latencies. Even 100 milliseconds has an impact on the business. So the notion of auto-scaling as a solution is non-starter. There is too much other things that I have to deal with. And auto-scaling them is hugely expensive. Now, what happens if I use a queue? If I use a queue, scaling a queue is trivial, mostly because queue doesn't do much. So from a user experience perspective, the frontend do some minimal validation on the message and throw that into the queue and says, okay, got that. We're good. If this is now this is where we start diverging based on the sort of operation that we have. We may tell the user, okay, this order is this operation is complete. For example, if I'm posting something to a blog, I may want to run that through spam detection. And that may mean that I have to take some time to do that. But the frontend could already put that comment in the blog, completely purely JavaScript code, which is fine. The user is happy. We will complete that operation. In some cases, for example, maybe I need to validate that your mortgage payment has been accepted, or validate that, or compute what is the new rate for your insurance after a new accident, something like that. Well, that may take some time, but I can put that concept of a queue directly into the UI, just like what they do in McDonald's. Your order is being prepared. So now I can say, hey, I'm computing your status. And just the fact that I'm showing you that, and hopefully also show you all of the stage that it goes through, gives me a huge amount of benefit. Now, here is something really funny. In the States, there is this concept of manually submitting your taxes. So every year, pretty much everyone has to submit their taxes. And there are a lot of software to automate that and make this possible. It turns out that when you hit the complete process on the prepare your taxes, many tax software will show you a window computing, optimizing, calculating, a bunch of other crap like that. Now, none of that is actually required. Computation for a single person tax or tax whatever is relatively simple and can be completed like that. The problem is that from the perspective of a human, that's too fast. That's not acceptable. You have to show them that work has been done. Again, this is completely unrelated to scalability, but it is important when we're talking about how human think about and value work. If it happens too fast, they don't value that. Now, so we store the message in a queue, and we have something in the backend that we're going to read that queue. Now, just from this point, we have some huge benefits. First of all, I can monitor the queue drain rate, how fast messages are being written, how much they're being read. If they have more written than read, I can add more workers. And that's exactly the same as autoscale, no? Well, not so much. Here is the deal. If I have a temporary spike, everyone wants to go and buy the Mona Lisa. I'm offering a 9 a.m. On the university where they give you the grades. Everyone goes F5, 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 stuff like that. How does it work in such a system? Well, in the university grades example, we are not showing the grades. And we're not querying anything. Maybe we're querying just the already prepared data. We don't have to do any work. In the case of everyone wants to buy the Mona Lisa, I have a spike of traffic, and then the queue and the queue processor is going to just go through that. In most cases, that's enough to smooth things over. I don't need to have better capacity because I get time to process that. There are other major benefits of queues. For example, I can make sure that all of my queue messages are logged. So I have automatic audit trail. I have all sorts of interesting things that I can do here. And note that there are privacy consideration to take into account. But from a technical perspective, this is an amazing feature. Now, here is another really interesting scenario. If I have a queue, I can approach the system in such a different manner. Remember previously I said about about Starbucks and baristas? Instead of processing one cup at a time, I can look into everything like give me 10 cups all at once. Or I need to steam milk for 6 cups. I can steam that in one shot right there. All of the work that I have to do for this batch of operations can be done in a batch-oriented manner. This can have huge impact on the overall throughput. Now, this is not something that I can do if I'm just processing requests, but using a queue, it is almost mandatory. It's becoming something that I can trivially do. And the cost of doing that, the cost per message is amazing. The amount of time and effort that I can spend. In the same sense, in many cases, maybe I can put I have a bunch of documents or a bunch of messages I have to process, and I can see that all of them are for Romania. So I'm going to send one request to the Romanian address validation service. Okay, that's great. Now, here are some other things that I can do. Instead of using a queue, I can start using specializations. Oh, I have this queue here for all of the purchases from Brazil. So I got a worker for that. And that's important because the Brazilian cells shouldn't be impacted by the fact that the Romanian validation code isn't fast enough. It also means that in some cases I can scale far far more accurately. I need better scale for the Brazilian locations. Just that. I can also analyze much more accurately what actually is happening. And again, spikes are smoothed. I know I repeated that, but this is important. This is important because it means that you can withstand things a lot easier. Especially the moment that you accepted that you're going to be processing in a synchronous manner with a queue. It means that your SLA is no longer 200 milliseconds. That's no longer the case. In some cases, my SLA can grow to be minutes. If I order something from from a shop, and they're under load, and it's going to show up in the mail next week, they actually have hours to process that. They don't need to run through everything. And even if you're talking about something that I expect to happen far more quickly, okay, give me the new rate for my insurance. Okay, I'm calculating that. It's going to take me a minute or two. And that alone has a huge impact on the complexity that you have to deal with, on the amount of work that you're working with, all of that. Now, there are other things. One of the nice things is that I'm also only doing pure computation. There is some persistence, there is talking to third party or whatever, but I don't have UI concerns. I have a very simple model of input and output. That's it. All of the typical complexities, caching, the session, authentication, user validation, all of that, that's the front-end job. I have far lower cost of work because I'm doing a lot less at the architectural level. Now, let's talk about some other aspects. What if I have a failure? I can just put a message back in the queue and retry. What happens if something strange happened? Well, I have the message. I can throw the message on my queue and debug through that. That's becoming something trivial. Now I have very easily all of my inputs. So things become much more predictable. From the point of view of operations, I need to upgrade the code to a new version. Well, spin a new worker with a new code. It started processing with the new stuff. Shut down the old worker, let it drain everything that it had currently processing, then you're done. This is a zero downtime operation. For that matter, because queues are so simple, they are also operationally easy to operate. Or I need to update the queue service itself. Trivial and easy. It also exposes a lot of metrics into what's going on. The time in queue, number of messages, the drain rate, all of those things are now things that I have the ability to act upon. It also means that I have this powerful ability into looking into the queue. What are you doing? I can tell. What have you been doing? I can look at the log of the messages. And from the perspective of debugging and understanding what's going on, that's crucial. A lot of that is also about limiting the blast radius of what you're doing. Because you're operating on just this location in the backend, or just this location in the front end. And you don't have to keep so many balls in the air. So what about the front end? I keep talking about the backend, how it's processing, but let's talk about how we are building the user interface, the server side that pull the data and everything. Most of that, you're going to just deal with chewed data that has been prepared. Now, some operations are insanely cheap, even on writes. For example, if a user wants to update their nickname, I don't need to push that into a queue and then wait for that and do all of the user interface around that. That's probably not relevant. This is something that is rare. This is something that is cheap. This is not something that I'm actually being measured on. The complex stuff, getting insurance quote, give me, I don't know, how much money do I have to pay for my mortgage, all of those sort of things, either already prepared or I send them to the backend to computer. Most of the frontend is just about the presentation, taking the data and throw that. There is a user experience challenge in how to do that properly because you have to figure out what is the expectation of the user. If I'm posting to a blog, I don't expect that, this would go into a queue and would work. You know what? Maybe if we Stack Overflow, for example, in Reddit, you have moderation queues. So that is an explicit part of the system. But this is now becoming a user experience issue, not a technical issue. And you have to sometimes explicitly push against doing expensive operations inline. I want a report. If you go to PayPal and says, I want to know how much money I spent, they make you submit a report request. And typically within 30 seconds or a minute, they have that ready. But I've seen that take half an hour. And that means that if this is tax preparation session, where everyone is going to PayPal and saying, give me the report for the last year, they're not suddenly having to triple the capacity of the system. A lot of that means that you throw it in the background and you just forget about that. It's expensive, so I'm not doing that. That's someone's SHO. That's the back end work. Now, waiting. Waiting is something that can be a superpower, which is strange because I spent so much time so far basically telling you that you shouldn't be waiting, that you have a hard time limit. So if the operation is trivial, don't bother. Make sure that this is actually trivial. Trivial defined as update one element in the database. That's it. Doesn't have to run computation. Basically, simple CRUN. It's more complex than that. Throw it into a queue. Now, it's okay to make the user wait as long as you're not making them wait for the acknowledgement. And again, I'm waiting for my order to be ready in McDonald's. I'm okay waiting for the food to be ready. I'm not okay waiting at the counter for the cashier to give me my credit card back. That's the difference. In some cases, you also have to consider, this is under 10 seconds. I can pretend that it happened immediately. Worst case scenario will pop up something to the user. And if it's greater than 10 seconds, something like that, okay, I need to make that into an actual queue, something that is visible to the user. And I call this an architecture superpower because accepting that gives you so much benefit in terms of how far you can go. They give you so much flexibility. Here is another superpower. I'm sorry, can't do that. Consider the case of a Black Friday sale. Lots of users wants to buy that. I have limited inventory. How do I do that? One of the ways of handling that is to say, okay, every time that I have a sale, I'm going to look on the inventory, mark it down, and continue. That's complex. That's really, really hard to do efficiently. And what's more, that's going to have impact on my entire system. Instead, I'm going to go the other way. Where I say, oh no, I'm going to accept all of the orders immediately. I want to make it easier for you to spend your money. So I'm accepting the order. Mark that I'm accepted, not processed. In the background, I have something that processes them. And if I have 10 concurrent processors instead of 50,000, all of them of separate requests, it's much easier to coordinate between them. And if I run out of inventory, I'm going to say, sorry, couldn't manage that. And I can give them an offer to another model. I can say, okay, sorry, we refunded your money. Here is a coupon code for the next time that I can actually give you more business. Now, this is a really powerful technique because it removes so much complexity from what you're doing. So you cannot do that. So all of your actual code, all of your users had an extremely pleasant experience until the end. And you can typically figure it out. You can go to the supplier and say, hey, can I get more TVs? Can I do that? Maybe, maybe not. Maybe I can do something else. Maybe I have to eat some profit in order to do that. But now this is a business problem. People give me money. I'm trying to fulfill this thing. This is no longer a technical problem. It's good that it's no longer a technical problem. Now, what happens if this is not something that I can do? I kept talking about selling the Mona Lisa. So let's talk about that. How can I manage to do something like that? I have 50,000 users who keep submitting auction. I have to assume that there is a very high degree of concurrency. And obviously there is one single winner. So here's what I'm going to do. I'm going to just throw that into a queue, accept the bid. Notice that I'm recording when that happened. I can also probably need to figure out what is the highest amount that I've seen so far and send that. But again, that's something that I might have to deal with. This is some global mutable state that I have to deal with, but this is pretty trivial to manage. Because at worst case, I have to do some a maximum between all of the workers that I have, all of the items that are currently accepting bids. Not trivial, but not that hard. In most case scenario, this is a race. An auction like that is inherently a race condition. Okay, I got all of them. What do we do with that? And here is the processing code. Get all of the items from the queue that reach by the cutoff date, sort them by the biggest amount. So those are all of the valid bids. This is the winner bid, and now I can process that. I don't have to deal with concurrency here. If someone is suing me about the Mona Lisa, I have a record. If I have complex business rules, I have to do validation. I don't care. I don't care about that. It's okay. I'm working on that. Notice how this has been a tremendous boon for me. I went from, okay, I have to deal with 50,000 concurrent users and somehow trying to figure out who is the winner at any given point in time, to, okay, find the maximum value. And I don't care about validation rules and whatever. And then just running this piece of code to find who the winner is. And now I'm done. There is another really important architectural superpower. Being stupid. If you're doing simple things, if you're approaching things in a stupid manner, you're going to end up with a simple architecture. Simple architectures make it very, very easy to create sophisticated solutions. For example, one of the major strengths for PHP is that there is no state. Every invocation of the script, you start from scratch. And it doesn't sound like this would be a huge impact. But this alone had a really, really important aspect on how people design PHP systems. Because now you have no state. That means that you have to store the data somewhere. And okay, I can use Redis, I can do something, but oh wait, now I have really easy scalability because I can just run more PHP script processors. And we have to resist adding any sort of complexity because any complexity would have a compounding cost. And I'm just basically throwing as much as possible to the background. Where I have the time to do that, I have the ability to do more interesting things. I have the ability to choose, okay, this processor is doing, I don't know, image manipulation things. I'm going to use this C++ library for, here I'm going to use Python for quick scripting and integration between multiple third party and stuff like that. It also means that I have this sort of two approaches for most of all of the issues that I have. If this is simple and trivial, I can just CRUD, throw that into the database, you're done. If this is more complex, throw it into a queue, the backend will handle that. The front end is simple, the backend is relatively easy, and all of the infrastructure is now, all of the complexity is now in the infrastructure. This is how you're able to get really scalable systems without running complexity. Now is the time for questions.
Okay, Oren. Thank you so much for your talk. It was really great.
Thank you. Thank you very much.
Okay. We have a couple of more minutes before we'll move into discussion, and I have a very interesting question to you. What like, if we summarize your talk, what you will recommend for our audience as one thing they will need to follow for, let's say, the next project?
One thing, invest in time machines. More to the point, it's easy to get into the mindset that there is one architecture style that can fit all operations. If you're talking about any system these days, you would typically have a backend services, a website, apps for iOS and Android. You may have integration with third parties, and each one of those systems require its own architectural style and behavior. What I've described here is how we typically build website services and backends. If you want to build a good architecture from the point of view of an iOS application, that would be a completely different thing, mostly because I would tell you that, oh, you still have queues, but now you're operating on your local state, and there is a background process that syncs to the cloud service. Notice that another important aspect is where are you starting from. So scalable architecture is one side is give me an application that can scale in terms of user, but there's also scaling in terms of the complexity. And applications that live for a long time tend to have additional features. And if you can sit and design the bones of the application, of the skeleton of the architecture up front, and then see how you fit additional patterns and behavior into the system, that's going to be a huge impact on yourself. Because the way that it works is that the more you can, the more you can define the skeleton of your system to what you're actually going to do, the easier it is to develop and operate on that. And I think that's the one of the key aspects that you have to consider, especially if you're at the team lead or architect positions where you can actually lay down how this is going to be.
Okay, sounds great. Thank you so much for your answer. And I would propose to everyone to move to discussion and dive deep into particular aspects there.
Okay, great. So thank everyone for being here. We'll move there and bye-bye.
Thank you, everyone.
Okay, so I'm signing off from speaker and switching to Zoom completely, right?
And me switching to Zoom as well, yeah?
Okay, bye-bye.
Okay, see you then.